So in last lecture, we started the discussion of semaphore. And in that semaphore, we discuss what is semaphore and how it can be implemented. Mainly, we discuss two types of semaphores. That is general or counting semaphore is one type. Another is binary semaphore, and how they can be implemented and how that semaphore can be used to achieve mutual exclusion between two processes or between multiple processes. That is what we discussed. And then we started the discussion of a simple program called produce. In fact, not simple, but rather I would say classic program called problem called producer consumer problem, uh, which you can see in a different, in different ways. You can see this problem posing before you, and if this kind of problem you ever encounter, you can always take the help of this semaphore to solve it. Today, if time will be there, I'll show you the implementation also. And we discuss what is producer consumer and what are the constraint and how it should work. And mainly this constraint that we discuss, that producer can't add data item into the full buffer and consumer can't remove data item from the empty buffer. And that is very simple to understand, but we just ease out this first constraint where we consider the infinite buffer. So there is no problem of full buffer, but gradually we will discuss also this constraint, and we will put this constraint again and we'll see how we can solve that. And then we discuss one solution. Okay, we discuss this solution, and we also discuss that in particular case this solution will fail. In this particular scenario, we discuss that the solution fails because the checking of n in consumer, it happens actually before it happens here, another producer runs and it changes that value of n. So when it checks n equal to 0, it is not going to be true, but actually it was true here. So that because of that, sometime after some time you will see that n reaches to minus value, which is not allowed. So this is what we discussed. And I also posed one question before you, that can we solve this problem just by putting this condition, just by checking this condition inside this critical section, because same weight B and same signal B, between that whatever you write, that is your critical section. So can I solve this problem just by putting this condition inside this? So have you checked that? Have you tried to work on that? Have you thought on it? Anyone? If I put this checking condition inside this critical section in consumer, will that solve my previous problem? I hope you are now aware what problem we are discussing. Anyone? Just let's try that. If I check this condition, if n equal to 0, same weight B delay, if I put it inside this after n minus 1 s, if I put that, what is the possible problem that it may create? What is the possible problem that it may create? For example, when consumers say n minus minus and it becomes 0, let's say it becomes 0, then what it will do? If this statement, if this particular statement is just after n minus minus and before same signal B, if it is there, it will check, oh yeah, n equal to 0, so I need to wait. I need to wait for delay to be signaled. So now consumer will be blocked inside critical section. Consumer will be blocked inside critical section. It means this semaphore S, it is not released. So inside critical section, this consumer will be blocked and it has not released semaphore S. And because of that, what other problem may be created? Because n equal to 0, so it has to wait for other data to be produced. Okay, I'll come to that question. Someone has asked some question. We'll discuss that. But just see, consume is not part of, first of all, consume method. It is not part of critical section because it has nothing to do with producer consumer or shared data. Whatever you have taken, let's say you have stored it in some, whatever data is there, you have stored it in some local variable and that you are consuming. That means you are using it somewhere. Maybe you are printing it. That's it. That is the meaning of consumption. Important thing is this. Should consumer wait further for any new data to be produced? If n equal to 0, it means there is no new data, so it has to wait. But if that wait is inside this, after n minus 1, if that is checked, consumer will be blocked. Consumer is blocked in critical section which has not released this semaphore S, and in that case producer will not be able to enter into the critical section, and it will not be able to append new data into the buffer. So as producer is not able to put item inside buffer, and consumer is waiting for new item for inside buffer, and because of that it is blocked. So now what is the situation? What this situation is, consumer is waiting for new data item and it is blocked. Producer cannot produce new, I cannot append new item in the buffer because it cannot enter into its critical section because S is not released. And because of that, semwait BS, when producer has called semwait BS, it is also blocked. So what's the condition is this? Consumer is blocked, waiting for new item. Producer is blocked, waiting for semaphore S to be released. What this condition is called? Deadlock. Exactly. So just by putting this condition inside critical section, it is in fact going to make it worse. It will make this process is deadlock. So that is something that we need to discuss. So this is the correct solution. Actually, it is almost same. It is almost same like this. Okay, the only thing is, rather than checking here n, which is a shared variable, you can see that it is a shared variable and it can be changed outside the consumer, right? Or by any other consumer also. Rather than checking the shared variable, first inside critical section, whatever is this n value, we will store this n value in some local variable, which is only for that particular consumer process, which is accessible to only that consumer process, local variable. So we will store that reduced new value of n to that local variable, and then we will check local variable. So you can see n we will assign to m, and then we will signal this, and checking will happen again at the end, but it will check only m and not the new value of n, because now you will get the actual value of your n that was there when you executed this critical section. Just by making this little change, now this solution is going to work perfectly. There is no problem. Where this S and D delay both are binary semaphore. Are you convinced with this solution, or you have any question on this? Do you agree? Please let me know. Do you agree with this solution, or you want to check this? You might have some question on this. Okay. So this is the correct solution. There is another version of this solution which is better. I mean, not better in fact, but it is clear than this. You know, this is little bit, still this is little bit clumsy. You can see the number of things you are doing here, right? Still it, you know, it is error prone, because there are very high chances that you can create, you commit some mistake in this program. So though this is the correct solution, the clearer version of that is this. Now you can see this solution. Here now n and s are the semaphores, and they are general semaphore. They are not binary semaphore. Like in this, whereas in this solution, S as well as delay both are binary semaphore, but now we are using general semaphore. And this will make it, this will make, this looks nice, this looks simple to understand. And you see this, how it works. Producer continue, I mean, there is infinite loop in producer, there is infinite loop in consumer. Producer produce the item, which is not part of critical section, so it generates some item. Then to put that item inside the shared buffer, it has to wait for semaphore S. So semwait S, if it gets that access, it will put that item in, in the buffer. Okay, and then it will signal the S that okay, I am done, and then it will signal that N. Now instead of signaling delay, what it signal N, it means some new item is produced. So n will be incremented. As you know, general semaphore, when you signal, it increments that value. It increments that value. So here n we are using rather as semaphore, general semaphore. So if it is increased, it will same signal. So new item, when it is produced, same signal n will be done. So this will tell that, okay, there is some new item at least. And consumer, again, it waits for n, that whether there is new item or not. If yes, then it will check S. Can I access this critical section? So if producer is not accessing critical section, or any other consumer is not accessing critical section, I can access that. Okay, if I can access it, I can take the value from it. So it will work on that buffer, it will get the value from the buffer, and then it will say, okay, I am done. So it will signal S. And then consume is the part of local process. It is not part of critical section. Do you think that this is simple to understand it and it is going to work? Yes, guys. Okay. Any question you have in this? Any question? Okay. If you don't have a question, let me ask you a question. If I change this order of these two statements in producer, same signal S and same signal N, instead of that, I put same signal N first and then same signal S. Is it going to make any difference, or is it going to make this code incorrect? What do you think? Is it going to create any problem, or it will work if I change order of these two? Okay, let me tell you one thing. If you do not give me answer, and if I need to wait again and again for that, there are two possibilities. Because I am the kind of person who are not going to complete this just for sake of completion. Okay, if required, I'll take more and more extra lectures. If you are not interactive, and if you are not going to respond fast, that is the possibility that I will take more and more extra lectures to complete the course. Okay, someone has answered. Same weight in consumer will be triggered first, and it will be stuck in weight of S. Okay, so you are trying to, you are answering this question that if I change this order, that can be a problem. Okay, so what you are trying to say that same weight in consumer will be triggered first, and it will be stuck in weight of S. I'm not getting your answer actually. See, if I first signal N, let's say after signaling N, and still S is not signaled, and let's say this producer is switch and consumer comes, can consumer enter? Can consumer enter in this same weight N? Yes, because same signal N is done, so consumer enter into this part, same weight N, fine, but then it will stuck here. That is what you are trying to say. Okay, fine, but is it a problem? Because then after, if it is stuck, after some time producer will get time and it will say same signal S, so this will be unblocked. Is it a problem? What do you say? Is it a problem? See, there is no problem, because this order, why it does not matter? Because consumer is waiting for both this semaphore before entering into the critical section. So in whichever order you signal this, ultimately it will be done. It will be done properly. Yeah, that is possible, that it may waste some time. It may waste some time, but otherwise ultimately it will be done. So that is one part. If I change this order of this two, it is not going to impact it much. The program is still correct and it will work. What about this? If I change this order, is it going to create any problem? Let's say this is like this, producer is written like this, and if I change this order, is it going to create any problem? Okay, someone says no. Let us try to scan this. Suppose here it has said SAM signal S. Okay, SAM signal S. And here it is SAM weight S. First is SAM weight S. So what will happen? After SAM signal S, if it says SAM weight S, which is done, okay, which is done. So SAM weight S will be cleared and it is not going to block. But then there is SAM weight N, which is not done, which is not done, right? Which is not done. So again, this will be blocked, and here after some time it will say SAM signal N, and this SAM weight N will be cleared. So there is no problem. But what if this order is changed as well as this order is changed? If I SAM signal N first and then SAM signal S, and here it is SAM weight S first and then SAM weight N. Will there be any problem? Now this answer I want from you people. If you want to answer it, you can unmute and you can answer also, no problem.
The situation may be same as this now. So just the order of S and N will be changed.
Okay. Okay, let us try to visualize this way. Suppose this order is changed. Forget about this order. Let's say it is this way only, because it is not going to make any difference whether it is in this order or alternate order, right? But let us think about this. Let's say consumer is somewhat, let's say it is inside the critical section. Suppose consumer is in critical section, suppose. Okay. So in that time, let us say okay, how should I explain this? Let me, okay, 1 minute. Suppose if consumer is in critical section, it means it has blocked both this, right? It has blocked this. Okay. Now, as it has blocked N as well as S, can producer produce the item? Can producer produce the item? See what is happening. Let me tell you this way. Here you say SAM weight S. Here you say SAM weight S. Suppose first is SAM weight S. Okay. Currently, there is no item. Just assume that there is no item. But SAM weight S, consumer is the first process which is executing. SAM weight S. What will happen to that? Will it be allowed to enter? Because this is the first process which is executing even before any producer. Tell me, if I say SAM weight S, will consumer be allowed to enter? No. Why no? As initially it is 1. S is initially 1. So at least one process can pass that test. It need not to wait. Are you getting my point? Okay. So if initially there is no producer, it means there is no item. N is 0. N is still 0. And first process, because there is no fixed order, which process will execute first, we don't know. So N is 0, but S is 1, and consumer is the first process to execute. And here, let's say instead of SAM weight N, you say SAM weight S. It means consumer will enter, and it will now next statement that it has, it is SAM weight N. Instead of this, it is now have SAM weight N. What will happen to this consumer SAM weight N when it calls? Here, second statement, if it is SAM weight N, if consumer calls SAM weight N, what will happen to consumer? Yes, what will happen to consumer? Definitely it will be blocked because n is 0. N is 0 and you say SAM weight n. So SAM weight S, fine. Consumer passed that test and it tries to now wait on n, but n is 0, so it will be blocked. So at this second statement, consumer is blocked. Now producer comes because consumer is blocked. Now producer will be given a chance. So it produce some item and then it will waiting for SAM weight S. What will happen at this point for producer? What will happen to this producer at this point? It will also be blocked. Now what is happening? Consumer cannot be unblocked until unless there is new item, but producer is already blocked because there is no S. So both are blocked and this is deadlock. So if you change order of this, then there is a problem. But if you change order of this, there is no problem. Does this make sense? Does this make sense? Okay. So this is producer consumer problem solution using general semaphore. But then this is the solution to infinite buffer, where we have assumed that buffer is infinite, but it is not the real world condition, right? That is not real world scenario. So what can be the real world scenario? Bounded buffer. Real world scenario is bounded buffer. It means you have fixed number of slots where producer can put the item. Okay. So in bounded buffer, that is called bounded buffer, means buffer size is fixed. How producer, where producer can be blocked in case of bounded buffer? If producer is trying to insert in the full buffer, so if the buffer is full and producer is producing new item, it has to block because it cannot put item into the full buffer. Whereas consumer will be blocked on empty buffer. If buffer is empty, consumer cannot consume item and it will be blocked. When producer will become unblocked? When some item is removed by the consumer so that there is new slot where producer can put the new item. Some slot has been emptied and producer can put new item, so it will be unblocked when consumer consumes some item. Whereas consumer can be unblocked because it is waiting for empty, it is waiting for some item, new item. So it will be unblocked when new item will be inserted. Are you getting these 4 things? Okay. So let us discuss that scenario. Let us discuss the solution for bounded buffer. So now just think that there is one size of buffer, okay, which is one integer, which is nothing but the buffer size. Let's say 10, 15, whatever is the buffer size. And there are semaphores S and N, and one more semaphore is used, E. E represents size of buffer. E value initialize, this value of E, initial value of E is nothing but size of buffer, 10, 15, whatever. And that is possible with general semaphore, right? So initially, let's say if this is 10, it means 10 items can be produced and appended in the buffer. Before buffer gets full, 10 items can be produced if even no consumer has consumed any item. So now if you see this solution, producer will produce item and then it will wait for E. Now E represent how many items it can produce without blocking. What E represent? It represent how many items it can produce without blocking. So initially size of buffer, so initially it can produce 15 items. So if it says SAM weight E, where E is let's say 15, will it be blocked or not? Tell me, will producer be blocked or not? Yes. What do you think? If E is initially 15, consumer has yet not run, and first producer comes and it waits on E, what will happen at this point? Yes, because E value is greater than 0. Even if you call wait on that, it will be reduced by 1, but still it is greater than 0, so it won't be blocked and it will be allowed. And definitely if buffer is not full, because what E represent? E represent empty slots. You can say empty slots. That's why it is E. E represent empty slots. How many slots are empty? That many items producer can append. So E is still greater than 0. That means empty slot is still greater than 0. So it can proceed further. Now it has to wait for semaphore S. Initially S is 1. So maybe it is allowed, and then it will append, and then it will signal S. But it is not signaling E. E is not signaled by producer, because producer, where E is the empty slot, so new slot has become empty. That information can be given by consumer and not the producer. Okay, producer, what information producer gives? That I have produced new item. I have produced one more item. That is the idea. So producer will signal N here. So just one change is here, that same weight E is added before same weight S from the previous case, because in previous case there was no bounded buffer, it was infinite buffer, but now empty slots are fixed. So that's why it has to wait for it. Similarly in consumer, this is same, but after same signal S, it will tell that I have consumed one item, so there is one more empty slot. There is one more empty slot. So that will be given as a signal. So by chance, if there was no empty slot and producer was blocked on that, this same signal E will allow this producer to produce new item. Does this make sense? Yes. Are you getting this? So how this functions, they will be they will be implemented. So you can see here, instead of this equating it with 0, you need to equate it with the mod n. In plus 1 mod n equal to out, then do nothing. Otherwise, put that item in the buffer and increment this in index, that is in plus 1 mod n. I hope you understand this modular operator, because this is bounded buffer and it is like circular queue. It is like a circular queue. Have you gone through this circular queue in your data structure subject? So you should be able to understand this. Fine. So this is semaphore that we discussed, and this semaphore, if you see, especially even in last example, it is very clear. What is the use of semaphore in this particular problem solution? For what purpose we have used semaphores here? To achieve what we have used semaphore? Can anyone tell me? One is achieving mutual exclusion. That is one thing. And which semaphore helps you to achieve mutual exclusion here? All these three, S, N, and E, all these three are helping you to achieve mutual exclusion. Mostly yes. Okay. S semaphore, right? It is helping you to achieve mutual exclusion. Then what N and E is for? What is the purpose of semaphore N and semaphore S? Can anyone tell me what is the purpose of semaphore N and semaphore E in this solution? E is to maintain free space in buffer. Okay. But if you see, producer is waiting on E, whereas consumer is signaling on E. And on the reverse part, producer is signaling on N and consumer is waiting on N. So basically this E and N, these are the semaphores which are used for synchronization purpose between producer and consumer. Synchronization means what? What do you understand by synchronization? If two people are working on something, some common task, there need to be some synchronization between them. Okay, one person says, okay, let me finish this, then you can do this, something like that, some kind of synchronization. So producer says that, okay, let me produce some item, then you can consume. And consumer says that, okay, let me consume some item, so there will be new empty slot and you can produce new item. So they are working in sync, and to achieve that synchronization between producer and consumer, this N and E, these two semaphores are used for synchronization, and S is used for mutual exclusion. Is this clear? Is this clear or not? Okay. So purpose of this semaphore in this particular problem is to achieve mutual exclusion as well as synchronization. There are two purposes of this different semaphores. Okay. Now, next we are going to discuss monitors, which is again some construct, programming language construct, which helps you to achieve same thing, mutual exclusion and synchronization between processes. Okay. So what is monitor? The monitor is a programming language construct that provides equivalent functionality to that of semaphores, and that is easier to control. See, whatever you achieved using semaphore, same thing you can achieve using monitor in a easier way. Okay. Monitor is implemented. This idea is implemented in number of programming languages, including concurrent Pascal, Pascal Plus, Modula 2, Modula 3, and Java. If you have done Java and if you have worked with synchronization, multiple threads and synchronize keyword, then you may be aware of this term called monitor. Monitor is nothing but it is like similar to some object. It is similar to some object. Okay. What are the characteristics of monitor? There are few. See, you just think this monitor as one object. Okay. How many of you are aware of object-oriented programming? Have you done any object-oriented programming language? Maybe C++ or Java. Okay. Which one? Java. Okay. Someone has done Java. So all of you have gone through this subject called Java. Okay. But okay. So have you gone through this multiple threading in Java? Multiple threading in Java, multiple threads. Have you worked? No? Okay, fine. So again, I'll show that, or I maybe give you that as an assignment in your lab, how you can use Java monitors. Internally it is using monitor. Okay, you need not to do anything special. Internally it is using. Fine. So you can think about this monitor as one object, which has some procedures, which has some methods and some local variables. Okay. Again, when I say local to that object, okay, that is instance variable. You can think in that way. So what are the characteristics of this monitor? Local data variables are accessible only by the monitor. Okay. Local data variables are accessible only by the monitor. Second characteristic, process enters monitor by invoking one of its procedures. Now process enters monitor by invoking one of its procedures. So whenever any process wants to lock, something, it wants to enter into the critical section. If it is executing any one procedure, any one function of that monitor, okay, it means it is entering into the monitor. So basically, I'll show you that structure. There can be n number of functions inside monitor. If any process executes or call or invokes any one function inside that monitor, it means it has entered into the monitor and it has locked that monitor. It has locked that monitor. And if one process has locked the monitor at a time, only one process can be there inside so that it can access critical section. And only one process may be executing in the monitor at a time. So these are the three characteristics. These are these three important characteristics for any monitor. So let us understand monitor first. It looks like something like this. Sorry. This is structure of a monitor. So this main box, it represents monitor object. You can think that way. So you can say it is monitor. as I told you, at a time only one process can enter into the monitor. So if multiple processes are there who want to enter into the monitor, there is a queue, because at a time only one process can enter. So there is a queue of entering processes and other processes are waiting in that queue. So you can see this is the queue of those block processes which want to enter into the monitor. Now this monitor has local data, condition variables, some functions and initialization code. So this is the part of any monitor: local data, condition variables, procedures, that is functions, and initialization code. Now what is this condition variable? Normally it is possible that if one process enters into the monitor, okay, now tell me how any process can enter into the monitor. How any process can enter into the monitor? What is the way to do that? We just discussed that. As a characteristic 2, we discussed that. What is the way? Invoking any of this one procedure, right? Process can enter into the monitor. So let's say some process is already there in the monitor and it is executing something here. Okay, maybe it is executing procedure 1. So at procedure 1, now it needs to wait for some condition to be true. Now it needs to wait for some condition to be true. Until unless that condition is true, it cannot go further. It means the process which is executing this code, at some point it is waiting for some condition. What will happen to that process which is executing that procedure 1 and it is waiting for some condition? So what should happen to that process? What should happen? Yes, block. That process should be blocked because it is waiting for something, some condition. So you can see there can be number of conditions possible, and for different conditions there are different blocking queues. Okay, there are different blocking queue. This urgent queue we will discuss, but for every condition there is one block queue. So if any process is waiting for any particular condition, it will be blocked and it will join this queue. It will. So now the process which entered in the monitor and executing this something and then it is blocked, it means now any other process should be allowed to execute in the monitor, or it should be allowed to enter into the monitor. Yes or no? Okay, so that is how monitor works. At a time only one process can enter into the monitor by executing any of its function. At any point, if any process which is executing the function in the monitor, if it waits for some condition, it will be blocked. According to that condition, it will be put in that queue and other process will be allowed to enter into the monitor. Now, and there is some initialization code, and one more thing is there, urgent queue, that is C signal. Okay, C signal means C wait is there. If any process is waiting for condition, it will call C wait. In semaphore wait, we have SAM wait, SAM signal. So we can understand that it is SAM wait and SAM signal. Here, not exactly same. I mean, of course, these are the different operations. But if any process is waiting for any condition on any particular condition variable, then it will call C wait. That is condition wait. So C wait when it is executed, and if that condition is not true, it will be blocked. But whenever there is a point, some other process may signal that okay, this condition, okay, for an example, if producer is executing here and it is waiting for empty slot, producer is executing and it is waiting for empty slot, there is no empty slot. So that is one condition. Producer is waiting on empty slot. So it will call C wait empty slot, suppose. And as there is no empty slot, it will be blocked. But then as it is blocked, consumer may chance to execute take process. And in take procedure, there is a point where it has consumed some item, so that it will say, okay, there is one empty slot. So it will signal empty slot. Consumer will signal empty slot. And as it signals the empty slot, the process which were waiting on empty slots, all those processes will be unblocked. One or more than one. It depends what kind of signaling mechanism is used. It's a simple or single signal, or it is broadcast signal. Based on that, either one or more processes which are waiting on that condition empty slot will be unblocked. And what will be happen, when it will happen, we will see. So you can see synchronization can be achieved by condition variables with the monitor. As we just discussed, synchronization between producer and consumer. Let's say this is append process function and this is take function. This is append function, this is take function from our producer consumer perspective. Producer is waiting for empty slot, so C wait empty. Okay, and when consumer consumes some or takes some item, it will say C signal empty. So this synchronization between this is happening through this condition variables. So synchronization achieved by condition variables within a monitor. Okay, and these are the functions for that. C wait as it suspends execution of the calling process on condition C, whereas C signal C resume execution of some process blocked after C wait on the same condition. Does this make sense? So basically we are trying to see how monitor helps us to achieve mutual exclusion as well as synchronization. Mutual exclusion is very easy to understand here, because at a time only one process enters into the monitor. At a time only one process enters into the monitor. So it means automatically mutual exclusion is there. Mutual exclusion is automatic because only one process enters into the monitor at a time. Whereas synchronization can be achieved using condition variables. They are achieved using condition variables. Does this make sense? Yes, guys. Does this make sense? Okay. So let us try to solve that bounded buffer problem. That is producer consumer bounded buffer. Let's see how it can be solved using Horse monitor. Horse is one researcher who has provided this design of monitor. There are multiple designs of this monitor. One of them is Horse monitor. We will see another monitor also, Lampert, and I forgot that name. Okay, but there is another design also. So there can be different designs, but let us first understand this solution from using Horse monitor solution. So just see this. This is your monitor. This is your monitor code, you can say. It has local variables. So these are local variables. These are condition variables. See, condition variables are mentioned using some data type called condition. Maybe in C we don't have this, right? In C we don't have condition type data type. Then monitor is bounded buffer. Bounded buffer is your monitor. Okay, bounded buffer is your monitor. And these are the buffer with the space n. Integer next in, next out, count is these are the other variables that we are going to use. And conditions are not full, not empty. These are the conditions, not full, not empty. And these are the two functions. These are the two functions which is part of your monitor. Okay, these are the two functions which is part of your monitor. And you can see append and take, because those functions which is part of critical section, those function you put it here, so that, as you know, monitor can be entered by only one process at a time. Okay, and that is how you can achieve mutual exclusion. So append is there, take is there. Now what is append? It will just check if count equal to n. Okay, if count equal to n, it means buffer is full. If count is equal to n, buffer is full. So it has to wait for not full condition. So producer, because append will be called by producer, so it has to wait for not full condition. So it will say C wait not full. So till then there is some empty slot. Producer cannot proceed further. So it is now blocked. At this point it is blocked. Okay. But if count is not equal to n, if it is less than that, okay, what it will do? Whatever new item needs to be appended, that item will be put at this point. at this index, next in index inside buffer, and this next in index will be incremented using this formula because it is circular queue. Buffer is your circular queue. So next in will be incremented like this, next in plus 1 modulo n, and it will say count plus plus. Count represent number of new items. Count represent number of newly produced items. So count will be plus plus. And there is signaling for not empty. So again, if you see this, this is similar to, not exactly same, this is similar to our semaphore N and S. This is N, this is S. This is E. This is E semaphore. So SEM weight E is same as C weight not full. And SEM signal N is similar to this C signal not empty. Not empty means I have produced some item. Then take, which is called by consumer, what it checks, if count equal to 0, it means there is no new item. I has to wait for not empty. Okay, so if producer produce new item, then it will tell me that, it will signal me that not empty. In that case, I will resume. Otherwise, it will be blocked. But suppose account is not equal to 0. What it can do, it can take item at this index from the buffer. Okay, and it will be incremented, it will increment this index by using modulo n operator and reduce the count and then signal not full. So now if producer is waiting for empty slot, this will signal it that, okay, I have consumed some item, you can produce new item. And this is initialization code. Initially, next in, next out, and count, all these three are 0. So if you compare this code with this structure, you can see local data is there, condition variables are there. These are the procedures or functions, that is append and take and initialization code. So everything is there. This is your local data. This is condition variables. These two are the functions, and this is initialization code. Are you getting this solution? And this is not final producer consumer. Producer consumer problem solution is this, where you have producer function and consumer function, which is infinite loop. Inside producer, what it calls? Produce item X and append item X. Append is part of monitor. Append is part of monitor. So whenever you call append, it means at a time only one process enters into the monitor. Okay. Similarly, consumer, take is the part of monitor. If you see, take function is part of monitor. So at a time only one can be executing in the monitor, and then consume. So this is the solution where append and take, they are part of monitor. Are you getting this? Yes. So now let us understand how this horse monitor works, because there are few characteristics that you need to understand. See, this is how it works. So let us assume instead of thread, you can consider as a process, because in Java, we don't have multiple processes. We have multiple threads. So in that sense, I have used here thread. Let's say thread A enters the monitor. This is entry queue. This is the entry queue, which is like this, entry queue. All the processes or threads which are waiting to enter into the monitor. So that is a queue for that. Thread A enters the monitor. That is step 1. And it is executing procedure A. It is executing procedure A. Okay. At this point, now it is waiting for some resource, condition variable. Let's say it is calling C wait some condition. So it will be blocked. Thread A will be blocked and put in the wait queue. It will be put in the wait queue. Thread B enters now, because at a time only one thread or one process, but the process thread A or the thread A which was in the monitor, it is blocked. So now new process can enter, which is part of this queue. So let's say thread B enters the monitor at step 3. At this point, it signals something. So thread B signals on the resource and enters the signal queue. Now this is interesting part. In horse design of this monitor, whenever any process signals something, that process itself will be blocked. That process itself will be blocked, and it will release the signal and it will be blocked. Block in the sense, it is not exactly blocked, but it will, you can say it will come, it will release that monitor. It will it is not going to execute further. So it will join this signal queue. After signaling, it says that, okay, now I am not going to execute. Let me give this chance to that block process which was waiting for this signal. So it will give chance to that blocking process, and that signaling process itself will wait in the signal queue. This is some kind of ready queue, okay, because process is not blocked. Process is not blocked, but it is giving its chance to that waiting process. So it will be joining this signal queue, okay, and then the process which was waiting on that condition, it will be unblocked and it will continue. It will be unblocked and it will continue. Okay, then after it will complete its job and exit from the monitor. So when thread A exits from the monitor, and let's say there is no other thread or no other process, and this process which was voluntarily released that monitor, it will enter back into the monitor at this point. It completes its job and it also exits from the monitor. And if there is any other process in this entry queue, that will enter into the monitor. This is Hort's design of monitor. This is interesting part. The process which signals, for an example here, as soon as producer signal not empty, it will release the producer. It is going to join signal queue. Okay, it is not going to execute further. Though, of course, in this case, there is nothing else after this. There is nothing else after this, so there is no problem. In that case, this will be completed. But suppose this after C signal not empty, if there was some code, that code will be executed only after the process which was waiting on not empty condition. If that process completed, then only that particular code will be executed afterwards. That is the design of Horse. So that's why in this design, what they have done, this signaling mechanism in both cases they have put at the end. So there is no need to wait for further code to be executed. Does this make sense? Does this make sense? Please ask your question if you have. Okay, a very good question. Someone has asked that, what if there were more processes in waiting queue? Will the process in signal queue allow all of them to execute if they are ready to execute, or only one? First of all, let's take this example itself. When you signal not empty, how many items can be consumed? Only one process can consume that. Yes or no? Whoever is asked this question, I am asking you. If, okay, so if producer says not empty, it means it has produced one more item. It has produced one more item. So this signal is for that newly created item, newly produced item. So only one process can consume that. Only one process, and that is actually the problem of this Horse design. That is the problem of Horse design. What is the problem? We will see that. What is the problem of this design and how we can solve that problem. So you have a good question. Just hold this question for a while, because we are going to discuss it further. But up to this point, is it clear? So what are the issues with this monitor, Horse design? If the process issuing the C signal has not finished with the monitor, that is what we discussed, right? Suppose here, after signaling, there is some more code. Let's say there is some more code to be executed. But what is the design of Horse code? What is the design of Horse code? It means as soon as it signals, it will join signal queue and it will give chance to other process. So what it says, if the process issuing the C signal has not finished with the monitor, then two additional process switches are required. One to block the process which is issuing the signal because it is joining signal queue. So that process switch is required. And when that process will resume, again one process switch will be required. So two extra process switching will be required in this design. That is one issue. Another issue, process scheduling associated with a signal. Process scheduling associated with a signal must be perfectly reliable. The question that someone asked just now, it is related to that. When a C signal is issued, a process from the corresponding condition queue must be activated immediately, and the scheduler must ensure that no other process enters the monitor before activation. Otherwise, the condition, okay, let me show it this way. Suppose here this process signals, thread B signals. As soon as it signals and it joins signal queue, the thread A, which was waiting on that condition, it should be immediately scheduled. It should be immediately scheduled and it should be given a chance to run. Because otherwise, what is the possibility? It has signal that, okay, this process can continue. But if this process does not continue and any other thread enters the monitor before that, that thread may change the condition variable on which it was waiting. It may block that condition again. That scheduling is very important. That as soon as this signals and join the signal queue, the process which was waiting for that condition, it should be immediately scheduled and get a chance to run. Otherwise, it is possible that before it gets a chance, another thread which has entered may have changed that condition and your code becomes incorrect. These are the two problems. Extra process switching is one problem, and another is scheduling must be reliable. Scheduling must be reliable, completely or perfectly reliable. Then only this horse design can be used. But if we want to cope up with these problems, there is another design called MESA monitor, overcomes these issues. What is MESA semantics? Now let us try to understand this semantics. Almost same, except this how signaling mechanism works. Thread A enters the monitor, it blocks at this point because it is waiting for some condition. Okay. Then thread B enters at step 4, it signals that condition, but it is not going to put itself in the signal queue. Rather, it will move. Yeah. Anyone is trying to ask? Someone has unmuted. Who has unmuted? Okay. So now, when this thread B signals on that condition, what will happen to that waiting process? That waiting process will join entry queue. That waiting process will join entry queue. Okay. It is not going to be immediately joining this. And this one, which has signal, it is also going to complete its job. It is not going to wait further. It is not going to join any other queue. It will continue. It will continue in the monitor. And this process, which was waiting on that condition, it will join entry queue. Okay, it will join entry queue. Then thread B completes and leaves the monitor. And then at 7, this process which was here, it will come back at this point. It will go through this. It is not directly coming here. Okay, there can be a design where this process will continue from wait queue to directly here. But this design says that it will first go to the entry queue and then come back. Why? There is a reason for that. This is also possible in some design, but this is better. Why better? We'll see. Okay. So, and then thread A, which was there in entry queue, now it will come here and continue from this point. Wherever it stopped, it will continue from there, completes itself. Okay. And if there is any other new thread which is waiting for monitor, it will join. It will enter into the monitor and continue. So you can see what happens after signal, that is different here. That is different here. Now the point is, the problem that we discussed in previous horse design, if this process which was blocked on some condition, and if B is going to signal that condition, but that process is not executed immediately. In fact, it is going to the entry queue. Don't you think that you may have some other processes or other threads in the queue before this? What do you say? Can there be some processes which are waiting before this in the entry queue? Yes. So it is possible that whenever thread B completes, instead of thread A, which was entered here, some other processes or some other threads, they will execute first in the monitor. Don't you think so? And if that is so, if they can execute before this blocking thread A, which is now unblocked, it is possible that they may change the condition variable. They may change the condition variable. Right? So what kind of change we need to make in this solution so that even if that happens, that if other thread changes the condition variable, the unblock process still work properly? What change you need to make? There is a small little change in this whole solution. Otherwise it is same. In Mesa's monitor, same solution works except one small change. Suppose this producer which was executing append, it was blocked on not full. It was blocked on not full. Then some consumer says C signal not full. So what will happen to this producer process? Where it will join? Which is unblocked. Where it will join? As per Mesa monitor, where this process will join, which is unblocked, just unblocked by consumer. Because of this signal, consumer has unblocked this producer, and where this producer will join as per Mesa monitor? Entry queue, exactly. But now before this producer process further, before this producer execute this code further, okay, some other producer has entered and it has produced some item, because it was also trying to check this, and not full is not, I mean not full is not true, sorry, not full is true, and another producer has produced the item and it has changed this condition not full to false. It means it has produced item and it has full the buffer. So when the unblock producer will come, from where it will restart? If that unblock producer will come, from where it will restart? From where it will continue? At this point? Yes or no? It will continue at this point. But before that unblock producer start from here, some other producer already entered in the monitor and it has already put new item, and because of that buffer has already full. Buffer is full. So in fact, this is going to be incorrect. This is going to be incorrect, because this producer thinks that I was waiting on not full, but as I am signal, it means it is having some space where I can put new item. But in fact, before it puts some new item, someone else has come in between and it has put the item. So it is going to overwrite some item, isn't it? Don't you think so? So what is the solution for this problem? Just small change here. And this same logic is applicable to consumer also. Small change. Only one word that you need to change. Can anyone tell me what change will make this correct in case of Mesa monitor? For this monitor, it is okay. Okay, for Horse design, this code is completely fine. But in case of Mesa monitor, small word you need to change and this will be correct. What is the requirement here? Before that unblock producer execute further, what is the requirement? What it should do? What it should do before this unblock producer continues at this point? No one gets the idea what it should do. Why it is becoming incorrect? Because it is not checking the condition again. because it is not checking the condition again. It should actually check the condition before start again. So what word you need to change? If you know C language, C programming, you should be able to understand that. What word if I change, that will make this whole program correct for MESA monitor? Seriously? I thought you people are smart people. Just make it while here instead of if. Yes, exactly. Instead of if, make it while. And you're sorted, because when that unblock producer will continue, it won't continue from here. It will continue from here. If count equal to n, again it will wait for that. Okay. So the whole solution will become true. The solution will become true just by changing from if to while. Otherwise it is same solution, no change. And if you want, you can do some refinements in this MESA monitor. Some other characteristics can be added. What it can be? You can associate some watchdog timer with each condition primitive. A process that has been waiting for the maximum timeout interval will be placed in a ready state, regardless of whether the condition has been notified. Suppose there is some producer or there is some consumer which is waiting for a very long time on some certain condition. Okay. So to avoid that starvation problem, what you can do, see, in this MESA monitor, it is not going to create any problem if it is put in the ready queue without any signal. If there is no signal on particular condition, but process is blocked on that condition for a very long time, just put it back into the ready queue, that is entry queue. Okay, directly, without worrying about whether signal has occurred or not. Why it is not going to create any problem? Because before that process will continue, it is definitely going to check condition again, because there is a while loop, so there is no problem. Okay, it is helpful to avoid starvation of that process. That is one thing, that is one refinement that can be done in this design. Another refinement is adding C broadcast primitive. The broadcast causes all processes waiting on a condition to be placed in a ready state, that is entry queue. Okay, rather than getting one process from that waiting queue and putting into the entry queue, whenever some condition occurs, whichever number of processes are there, let them go to the entry queue, because at the end only one process is going to get the chance. But we don't want to decide that. Let them go to the entry queue. And again, there is no problem, because MESA monitor checks condition before continuing. So there is no problem. And this is convenient in situations where a process does not know how many other processes should be reactivated. So these are the two refinements that can be done in MESA monitor to achieve something better. Okay. So now if we see what is the difference when we compare semaphore versus monitor, what is the difference? Semaphore is an integer variable s, monitor is an abstract data type, kind of object. I'm not saying it is exactly object, it depends on the language, but it is kind of object. So you can consider it as an abstract data type. What is the extent? The value of semaphore s indicates the number of shared resources available in the system. The value of semaphore s, it represents how many resources are available to be executed by that many processes. So if s equal to 5, it means there are 5 resources, 5 printers are there, and at the same time 5 processes can be using those printers. The monitor type contains shared variables and the set of procedures that operate on the shared variable. Access wise, when any process accesses the shared resources, it performs wait operation on S. And when it releases the shared resource, it performs signal operation on S. That is how semaphore works. But in case of monitor, when any process wants to access the shared variables in the monitor, it needs to access it through the one of the procedure or function of that monitor. And condition variable, if we talk about that, semaphore does not have any condition variables, monitor has condition variables. So in short, if I tell you, if you want to achieve mutual exclusion and synchronization using semaphore, for each of this, you require one semaphore. If you want to achieve mutual exclusion in monitor, it is implicit. You need not to do anything for that, because the programming construct of monitor is such a way that at a time only one function can be executed from the monitor by one process. So mutual exclusion is automatic. There are condition variables to achieve synchronization, the way we just discussed. So if you can now, if you have understood these two concepts very well, now you should be able to compare them. What is the semaphore and what is monitor, how semaphore works, how monitor works. Again, monitor, we discussed two different designs. One is horse design and another is Mesa design. So I think now you should be able to understand this very well. So we are done with semaphore and monitor both. And next we will discuss message passing. That it will be this message passing and reader writer problem we will discuss in the next lecture. Are you clear up to this point? Everyone. Again, I am repeating myself, but I suggest you read the book. Read this and try to see if you have any doubt or question and just put it across here. So if you ask question, then only you will get the answer. Of course, there is another way you can find the answer by your own. That is one way. But if you do not want to do that, or if you are not able to do that, read and find out the problems or difficulties that you have and just put it here. I'll try to answer that. I have programs for this. I wanted to show it to you, but we don't have enough time right now. So I'm thinking that you will do these programs in your laboratory. Okay, I'll give it to the Priyesh sir, the problem statements, and you will be doing it in the laboratory. So you will get the idea how this semaphore helps to achieve this solution. You are going to implement producer consumer problem using semaphore, and we are not going to create multiple processes. In fact, you will be creating multiple threads, because when you want to share something between processes, it requires shared memory. But in thread, it is very simple. Fine. So I'll discuss that with Priyesh sir, and you will get your problem statement. Okay, so let's stop this today.